welcome to part 3, the final part of the water vapor equilibrium series. In this video, I'm going to take the data we extracted from the Dortmund Data Bank website in part 2 and fit it to the parameters of the Antoine equation to make a model. The Antoine equation describes the relation of vapor pressure and temperature of pure liquids. It's the log of vapor pressure is equal to A minus B over C plus T, temperature, where A, B, and C are parameters, they're constants that are associated with their specific substance. So in this code, we will be able to fit our data to Antoine's equation by finding these parameters. Alright, so as you can see, we've got all of this stuff still from part 2, and now we're going to continue on to part 3. Okay, so the first thing that I've typed here, I've already got, is, so we have, if you remember from part 2, this data array, and it's just all of the temperature and pressure values from the Dortmund Data Bank. So what I have here is I've defined T, which is temperature, as the first set of data values in the array, which are the temperature values. And then I've set log PV as log base 10 of 1,000 times the second set of numbers in this array, which, just to point out, 0 is the first value of Python index, and then 1 would be the second. So so obviously it's the log of these values because that's what we want for Antoine's equation, and then I also multiplied it times 1,000 because these values are in kilopascals and we want them in pascals. Okay, so let's go ahead and plot this, okay? And we're just going to do one column and one row because we only want one plot right now. Okay. And then it's going to be a scatter plot. Our X is our temperature values and our Y is our log of vapor pressure values. Okay. And then we're going to do it in mode markers, scatter plot. Okay. So let's do, I think the only thing we need to add to this is just the update. And let's do it 700 by 500. Okay, that should be good. Yeah. Okay. Oh, we do need to add some axis labels actually just to make this look a little more professional. Okay, but let's just go over what we've got. So I did fig equals make subplots, rows and columns of 1, which if I were to do multiple rows or columns, I could have made multiple plots on here, but obviously we only want one. And then it's a scatter plot, so I did fig.add underscore scatter. Our x-axis is the temperature values, our y-axis is the log PV values, so this is a node marker since it's a scatter plot. And then this fig dot update underscore layout is just the width and the height of the I would call it picture because it's not like the axis or anything, but and that's decent size. So let's go ahead and add some labels to this. And then we should be able to move on to the next part. So food update underscore layout. X-axis. And temperature, that's what the x-axis is, and that's in kelvins. And then we want to do y-axis, color, and we're going to make that log base 10, vapor pressure, and that is in pascals. Okay. There we go. All right. So now that we've got our data plotted on the T versus log PV graph, we are going to make a line to fit this by finding those parameters I was talking about, A, B, and C, to fit our data to Antoine's equation. So I'm going to start out by defining a function. So we're going to call it model of A, let's say for A, B, C, and T, okay? And then colon, equals, and we want to return, and so this is where we actually put the function. So this is just Antoine's equation, which is A minus B divided by C plus T. Okay. So now whenever we use model, it's going to take those inputs, do the calculation using this function, and then have all that it's ready to go. Okay. Looks good. And then we're going to start out with some guesses for the parameters. So I'm going to call those A guess, B guess, and C guess, and I'm just going to enter some random values that are in a ballpark, I guess. And then I'm going to put those in an array called X sub mod. So A guess is equal to 10. B guess equal to 1500. C guess, and again these are pretty much arbitrary. What is it? Okay. And then we're gonna do that except equal to, we're gonna make that array. And that's just the A guess, B guess, C guess. Okay. Alright, and now I'm going to define another function for the sum squared error, okay? This is fitting to Antoine's equation. So I'm going to type and then I'm going to explain a little bit as I go, a little bit after I'm done. So what we're using here is we're defining this square error function, and our inputs are that X array, T, and the log PV. You make sure that my need to make sure that my variable names are not PV. I just want to double check. Log PV. Okay. Alright, we should be good. So now we're going to use this model function, and for A, B, C, and T, we're going to use involves the A guess, B guess, C guess NT. So we're going to do X, that X array, 0, because that's the first index in Python, then X1 and X2, because that's our A guess, B guess, and C guess, and then obviously the temperature value. So let's go ahead and do that. Let's see. Well, we're going to call that model PV. And do it the model function of X0, X2, and then T. Alright, so now we've defined model TV, okay? So now we're going to define the error. And this is when we're going to use that JAX, so JNP dot, well, let me type this out. The sum of model PV underscore syntax. Minus that squared. Okay. Yes. So basically, what this is, this is going to be our sum squared error. Okay. So we have we've defined model PV as that model function of our A guess, B guess, C guess, and T values, and then our error is the sum, and this is that JAX import point sum, which sums up those model PV values, okay, minus the log PV values. So that in itself is that deviation, either above or below the actual points that we already have on the graph. That's what that's going to calculate, and then we're going to square that because some of those are obviously going to be negative, but we want to get rid of both, and then we're going to add all those up again. That's the sum. Okay. Then return error. And I'm hoping that my syntax is correct for all of these. Yes. Okay. So now we're ready to. Oh, well, we need to minimize that error first, and then we'll plot. Okay. So let's do result equals minimize, because again, we want to close that gap. We want to make a line that fits our data. Okay. Square. It's not equals x not. Arguments are t and log of PV. Okay. And then the tolerance of 1 times 10 to the negative 10. Okay. And then we're going to use the gradient function from JAX for the sum squared error. Okay. I'm going to output that as well. Okay. I'm just going back through. Looks right. Okay. Alright. So now that we've got this, we're minimizing the function, and that's what equals result. Okay. And then we also want to add in something, we're going to call it T model. And this is just going to add in some, let's see. Yeah, I'm defining it as T model, but what we're doing is we're just going to create some more points just to add to our line to make it more nice. Okay, so JMP dot space, that's the function that we use to do that. And between T, the first T value, so T0, and the last T value, so T -1, we're going to add in, let's do 250. Okay. And that gives us 250 points between our first X value and our last X value. Okay. So Shift Enter. So now we're gonna call this, okay? Fig dot add scatter. Syntax. Okay. X is equal to our T model. Our Y is equal to model. No, it is going to be lines this time. Okay. Oh. Okay. All right. Beautiful. Okay. Okay, so this is another scatter plot. Let's go back to this one. Obviously, exactly the same thing. Do a comparison. This time we've got this line going through, and that would be our line that fits Antoine's equation, okay? So, yeah. Let's just run back through everything that we've done in this video. So, this was a little bit of a longer one. Again, this was all part 2, extracting that data and then putting it in an array. Right here, we stored the first set of data in that first set of data in the array as T, and then that second set of data, we took the log of, we multiplied it by 1,000 to change those units to pascals from kilopascals, and then we took the log base 10 of that for our log PV value, and then we plotted that. Okay, so we have our plot of temperature against log PV, and then we made some guesses of the A, B, and C values of Antoine's equation. We defined Antoine's equation using this model of A, B, C, and T. And then we took the sum squared error of our guesses in the equation and our actual data points, and we minimized that to create a line. We added in some points, and then we plotted that. And it looks beautiful. So, yeah, thank you for watching our 3-part series.